Welcome to the fourth online lecture on energy and potential. In this presentation, we'll be studying how electric fields. Remember, electric fields are force per charge fields, so you can loosely think of them as force fields. How are they associated with potential energy? Well, we know from circuits that volts in terms of units are joules per coulomb, and joules are Newton meters. So somehow potential energy per charge is related physically and mathematically to force per charge. Let's see if we can make that relationship a little more clear, and how do we compute potential from electric fields? Why are we studying energy and potential? First of all, energy is measurable directly in terms of volts. Energy, or energy per charge, is a scalar quantity, and the electric field is a vector quantity. How are the two fields related? In particular, how is an energy field as a function of position related to the electric field, which is also a function of position but is a vector quantity? How do you get a scalar field from a vector field? And how do you get a vector field from a scalar field? Practice in setting up and computing a new type of integral, the line integral, is another reason for studying energy and potential. And of course, there's the practice in computing and setting up gradients. Our objectives for this study are, first of all, to understand what voltage is and also reinforce the concept of work. We'd like to also explicitly relate the voltage to the electric field using integrals and derivatives. And then we'd like to find a new way to compute the electric field from a distribution of charge. So far we can do that using Coulomb's law, using Gauss's law, and now we're going to find a new way to do it. In order to understand energy and potential, there of course are the maths and physics background prerequisites. For math, we need to be able to do a line integral, which is related to our understanding of a dot product. We need to know what a line integral is and what a line element, a little piece of that line, is. In general, it will be a curve. We need to review the gradient vector from 253. We need to know what a differential is, like dq, dv, and so on. And we have to be able to work in both rectangular and spherical coordinates. From the physics side, we need to know Coulomb's law, the electric field of different charge distributions, the principal definition of work, and when does the potential energy of a system increase and decrease. In order to help us understand the mechanics of computing the work using electrical charges, let's appeal to a gravitational analogy. We have a mass m in the presence of a gravitational field, G, which is pointing downwards. There's an attractive force also pointing downwards of this amount here. And now what we'd like to do is take that mass m and lift it up and figure out how much work we do in going from z is equal to 0, z is equal to d. So let's lift it up. Here we are. There's the mass. We've lifted it up a distance d. And we can see that the work done is F dot dl, but there's a minus sign here because it's work done against the field. The dl is given by this little piece. We're moving only in the z direction. And now we're ready to compute the little element of work that we do against the field right here. We've talked about dl, we've talked about F, so it's a simple dot product of these two to give us the element of work done. Now when we do that, we expect that the potential energy, of course, will increase, and also we can see we have a new kind of integral to do here. This is our line integral. When we do the integration, we get the result mgd. If this minus sign were not present, we would get nonsense because we would get minus mgd. Yet we know that the potential energy has increased, not decreased. So now we can see the importance of the definition of the work done against the field to increase the potential energy. Let's continue the analogy. In the presence of the attractive gravitational field, we computed the potential energy increase in lifting the mass m from z is equal to 0 to z is equal to d. But for any generic z, the potential energy increase would be W is equal to mgz. So to get the force, what do? And this is a general principle for these kinds of fields. We're not losing energy in doing the increase process of potential energy by doing work. Take the negative gradient of W. If you do that, there's the negative gradient of W. There's W. The gradient operation involves the three partial derivatives differentiating mgz. We get mg. It's in the z direction, and don't forget we have this minus sign here, and that's equal identically to the force that we started with. No surprise, but it will help us later when we come to discuss electric fields. With the gravitational analogy behind us, we can now turn to the electric case. So now if we move a charge Q in an electric field E along some electric field lines E along a vectorial length element dl, we have to do some work, and the work is equal to the force, which is QE, dotted with dl because it's the force in the direction that we're moving, so it's the projection. And again, don't forget, we have, this is the last time I'll say it, we have this minus sign here in order that we have a consistent result, as we mentioned previously in the gravitational example. To get the total work done, we move the charge from 2 points, P1 to P2, and we get the difference of potential energy between the points P1 and P2. Now, it can be shown, this is for the mathematician, that for every path from P1 to P2, we will get the same result for the integral in 2. Also, I think it's very clear that the concept of potential energy difference is visible in equation 2. Here we continue with our discussion. The total work done in moving from 2 points, initial point P1 to final point P2, is this integral along this line element, the force projected onto it, because it's the force in the direction of motion that gives us the work done. In general, dl could be some line element, a piece of a curve. So it could either be rectangular, which is this one, rectangular line element, a line element described in cylindrical coordinates, or a line element described in spherical coordinates. Continuing on, we want to look at the work per unit charge. So here's the difference in the work done in equation 3. And now we divide by Q, both sides of 3. Work per charge is V, the voltage. So now we get the voltage difference in going from point P1 to point P2. We would also like, and it's important in many engineering problems, to have a reference potential. So it turns out in 3D, true 3D problems, we choose P1 as a point on a sphere of radius r that's infinitely far away. So the radius of the sphere approaches infinity, and at that radius we choose the potential to be 0. It's a little more difficult in cylindrical coordinates, but we'll talk about that in classroom activities. We continue with the previous discussion. We decided that in a true 3D problem, V of P1 is equal to 0, so it no longer appears on the left-hand side, and we have V of P2 depending on where P2 is. So for every choice of P2, we get a different value for the voltage of P2, reference to infinity. Now, if we move it around in 3D space, we can collect the potential field map or the values for each value of P2. And then we can write symbolically that P2 is a generic point x, y, z. And we have then equation 6, which really says we have a potential field map depending on how we do that integral. It's now time for an example. We're going to look at a parallel plate capacitor where we have two plates separated a distance d. The top plate is positive, the bottom plate is negative. There's a uniform field as indicated, and the form relationship is that E, as you can see from the slide, is minus sigma over epsilon naught times the unit vector AZ. This is exactly like our gravitational case. The force is minus mg times Az pointing downwards, and when we wanted to increase the potential energy, we went from Z is equal to 0 to Z is equal to D, and the potential energy was mgd. If we look at our capacitor, we can see that it's exactly the same. The force per charge, E, is down. We're integrating from 0 to D, and we substitute in the dL's the same. The minus is canceled. There's a constant here, sigma over epsilon naught. We just have a simple integral to do from 0 to D of 1, which is D. We pick our reference potential. Just like in the gravitational case, the mass had no potential lying on the surface of the Earth. We pick the same here, that V of 0 is equal to 0, and we get the analogous result that we got before using electrical examples. So analogies are very important in helping us to understand if we're doing things correctly. Okay, let's do a couple more examples. What's the next one to do? It's a point charge Q located at the origin. From Coulomb's law, we know the field here. We have spherical symmetry, so for any point on a XYZ lying on a sphere of radius r, the electric field is the same. So we're going to pick our line element to be a radial line element pointing away from the charge. We're going to be integrating from infinity coming into a point capital R. How much work do we have to do? Well, here it is again. Here's your F per charge, your electric field. And here is your line element. We're bringing a unit test charge in, so the force per charge is just the source charge Q. We do the dot product. That's 1. We integrate minus 1 over r squared, which is 1 over r from infinity to capital R. We're doing work against the field, so you can think of like compressing a spring. And you can see we get 1 over r evaluated where we stop at capital R. And that's the potential energy of a point charge with the reference at infinity. Now what's interesting is if capital R goes to 0, we got problems because all of a sudden the potential energy is infinite. Physically, this is nonsense. Some very bright people by the name of Richard Feynman, Shinichiro Tomonaga, and Julian Schwinger worked on this question and got the Nobel Prize in Physics in 1965. All right, now let's look at a harder one. This is like a 3D charge distribution. So we're going to have a general charge distribution, rho of x prime, y prime, z prime. We want to use our previous result for a single charge. Now, in the previous example of the point charge, r was the distance from the charge Q at the origin to the measuring point. But now r is the distance from any source point to the measuring point. So you can draw a picture here. Here's some axes. And here's the observation point. Say some observation point, call it A. And here, and this vector here is r. So what we have is we have another vector here, pointing to a little blob of charge. There it is, and this vector is r prime or r dash. So it's the distance from r prime to r, from the distribution, charge distribution, to the measuring point A, and that's what we see here. This is the r. It's the distance from the charge to where we end up. So r now is exactly the Pythagorean distance from a little blob of charge that we see here to the measuring point at A. And we notice that this blob is going to be some charge density times the volume density, volume element, d nu prime. So an element of potential is dq over r. That's exactly the same as this. See, we have potential charge divided by distance. So element of potential is equal to element of charge divided by distance from where we are to where the charge is located. Now this element of charge is equal to this quantity rho times dV. The primes indicate we have sources. Otherwise we get confused. We have to denote the source position somehow, and it's usually done with using these little primes. How do we get the total potential energy? Well, we integrate all the little dV blobs. Okay, we integrate those, we get V. We integrate the effects over all sources. So this is quite amazing. We now can compute the potential due to a continuous charge distribution in 3 dimensions. All right, so far we've been dealing with computing the voltage V as a function of where we are, x, y, z, given an electric field. That's shown in equation 14 on this slide. But we'd like to know how to go the other way. Given the electric field, we know how to compute the line integral 14, but what if we want to go backwards? In other words, you have the left-hand side of 14, which is V. How do you define E? How do you compute it? In order to do that, we go back to our gravity analogy. Here we see that we computed when we raised the mass from z is equal to 0 to any generic z, that the potential energy was mgz, a positive number. In order to get the force, what did we do? We took the negative gradient and we recovered the force. So in 13, we can see the same thing. You take the negative gradient of the potential to recover the force. The only difference is that this is work per charge, joules per coulomb. This is force per charge. So you cancel out the units of per charge, you get exactly what we had before. So now we have all the equations of electrostatics. We can see that 13 and 14 are kind of opposites to each other, or I loosely use the term inverse. This is not a formal mathematical inverse. It says if I have E, I can do this line integral for many different points x, y, z and get V. Then if I have V, I can take the gradient and get E. So we now have, with 13 and 14, all the equations of electrostatics. All the math is done. Let's do another example, our good old friend, the dipole. Well, we revisit the dipole, this time calculating first the potential, and then we will take the negative gradient to get the electric field. So here we are. Here's our dipole that we studied before. It's clearly defined with coordinates for the positive and negative charge. Positive at 0, 0, d over 2. Negative at 0, 0, minus d over 2. We're at an observation distance r from the origin at the point P. Coordinates x, y, z. And again, we have this condition that d, the separation between the charges, is much smaller than the observation distance. Again, we see the geometry of the dipole. I've indicated everything we needed when we used Coulomb's law before. Now we just need the distances. We don't need unit vectors because we need to find the distance between the source points at plus q and minus q to the observation P. And then we can quickly write down the potential. The distances are given by these two equations. And in the next slide, we're going to write down the solution. Here we see the geometry diagram again, and we have the distances from the charges. Positive charge, R1, magnitude of that vector, magnitude of the R2 vector in red, and we substitute that into the expression for the potential. We'd use superposition and add up the potentials of each of the charges. And we can see here something very simple. We have the difference between these two Pythagorean distances with the distance from the negative charge to the observation point highlighted in red. And now we're going to do something similar to what we did before in the dipole calculation when we computed the electric field. Well, in the center of this slide you can see the solution for the dipole, and I've highlighted again the z position in red. We define our function like this as before, and we can see very clearly that the first term in braces is the function like this, with z replaced by z minus d over 2, and the second term is z plus d over 2. We have a function evaluated at two nearby points and subtracted. So we're going to proceed very similar to what we did before. I'm going to lay out the explanation in a little more detail to review your understanding of derivatives and slope. All right, let's look at our result. Here we see what we have. This is from the previous slide. It's the difference of those two functions. First thing we're going to do is factor out a minus sign. So this says f at a little bit of z bigger than z at z plus d over 2 minus f at a little bit less than z, z minus d over 2. We'll call that the rise. So here's our rise. Now the run is the difference in the independent coordinates. So the difference between those independent coordinates is d. So we write the above here as the rise. This is just the rise here. So we write it as rise over run times run. So it's still the rise. But the point is that the rise over the run is the local slope. Now the local slope explicitly now is given by this expression. The rise over the run. And if d is really, really small, this is an approximation to not the total derivative because x and y are fixed, but the partial derivative. And of course here, d, that's the run. So really all I've done is taken the rise and multiplied it by 1. The run over the run. Run over run is equal to 1. But if I group it differently, we get this nice result. So we have that v is equal to this constant, including the minus sign, times the derivative of f times d. So now let's finish the algebra in the next slide. All right, now we just do the algebra. Here's our expression for our dipole potential, assuming that d is much, much smaller than the observation distance, which is given by the Pythagorean distance square root of x squared plus y squared plus z squared. Here's our function f. This is a very simple chain rule explicitly done here. There's the minus sign. It's going to cancel the minus sign up here. The 2's will cancel out. Combining all these results in 17, 18, and 19, we get equation 20, which is the final result. The only thing we have to do is to convert it to spherical polar coordinates, which we do in the next slide. All right, now we do the final conversion, and that's very straightforward. Equation 21 is just a repeat of the solution we got on the previous slide. We know from spherical polars that z is r cos theta. R is just the Pythagorean distance to our observation point. So we just substitute in simple algebra. The r from the numerator here cancels one of the r cubes down here, and the cos theta's up here from this part of 22. And down here we don't have r cubed, we have r squared because of the cancellation that I just mentioned. So now we're finished. We have the potential of a dipole in spherical coordinates. Well, what would we like to do next? Let's see what the next slide holds for us. Well, here we have the dipole potential V. We can calculate the electric field. How do we do that? Take the negative gradient as we talked before. Now the gradient of V when we're looking at spherical coordinates is this messy thing here. Nice enough, due to symmetry, we don't have to worry about this term. There's no longitude dependence because the dipole looks the same regardless of the longitude angle, so this term goes out. It's 0. We don't have to worry about that. Therefore, we just have to do an r derivative here and a theta derivative here of V. So when you do that, and don't forget the minus sign, because when you do the derivative of r to the minus 2, you'll get minus 2 r to the minus 3, but the minus sign gets rid of that. And the same when you differentiate cosine, you'll get minus sign, but the minus sign from the gradient gets rid of the minus sign from differentiating cosine. And so you simply get, simple differentiation gives you this, which is really what we got before using Coulomb's law, different way. It's summarized all in the next slide. Well, here's the summary. This is just a repeat of what we have on the previous slide. We have the constant QD over 4 pi epsilon naught. I've separated out. We have the 1 over r cubed dependence for the electric field and this angular term here. This is exactly what we got previously when we used superposition and Coulomb's law. And we applied that same derivative trick, but we had to worry about vectors, and it was a lot more complicated. Certainly, the V calculation was easier for the dipole because we're dealing with scalars. But we needed to pull out the gradient operation in spherical coordinates, which is not readily known. How would you derive it if you didn't have it in the book? So which method do you like? Do you like the direct method with a slightly more complex amount of algebra, or do you like this other method where V is easy, but finding the gradient isn't so easy? That bears some thought. With this, we finish all the examples. We've done a lot. We've done the parallel plate capacitor, the voltage across it. We've done the potential of a point charge. We've done the potential of a continuous distribution of charge. And then we revisited the dipole to see if we would get the same result we got previously for doing the electric field calculation directly. We also reinforced the idea of using the rise when the points are separated by a small amount to approximate the rise in terms of a derivative times the run. So basically, to reinforce, rise is equal to slope times the run, which is really delta y is equal to m delta x. from y is equal to mx plus b for a straight line. The only difference is m here is the tangential slope, instead of the global slope, m, which is constant all along a straight line. Well, here's a summary of what we did. The electrical potential V can be computed as an elementary line integral of the electric field. All the calculations rely on the fact that the potential of a point charge is given. It's Q over the distance, in this case R, from the point charge to the observer. More complicated distributions of charge are obtained simply by superposition, i.e. add them up, integration. And it is simpler to compute the potential because it's a scalar, and then take the negative gradient to compute the electric field. And that sums up what we did in this online lecture on energy and potential.